To an exciting section today. I can't wait to get started. This for me is really one of the most intriguing sections for me because I use this so much in my research and my everyday teaching as well, and that is integration, integral calculus. So far we've been looking at differential calculus. Again, very exciting. We need that stuff to understand motion, mechanics, and equally important is the concept of integration. So before we dive into integration, let's just slow it up a bit and look at something called antiderivatives. Okay, so we know what we mean by the derivative of a function. I would also appeal to you to go back to the videos on differential calculus, look at the concept of a derivative, look at the laws, and try a few examples before we get on to what we call antiderivatives. Okay, so I'll just quickly remind you of what we've been doing so far, and then we'll move on into new territory. Awesome stuff, man. Okay, guys, so you're familiar with the derivative, and here, basically, I think it's very important as well that we understand the notation. So f prime of x, we know, means df dx given a function f of x, like say x squared. Df dx is nothing more than differentiating this function f of x with respect to x. Keep that in mind. This is extremely important because we will be introducing to you new notations representing what we call the antiderivative, and later on what we refer to as the integral. So the notation is extremely important in this section over here and the ones to follow as well. So let's get into it. So let's look at a very basic example. Take a function f of x, and I think we're familiar with this. Let's go x squared plus 2x plus 1. And if I asked you to work out f prime of x, this is pretty straightforward. It's 2x plus 2. We're using, obviously, the power rule. We can even get the second derivative of this function, f double prime of x, with no problem whatsoever. And even the third derivative, which is f triple prime of x, and that's a constant. So if we differentiate f double prime, which is a constant, to f triple prime, I'd get 0. Straightforward, and this is nothing more than df dx. The point here is, can we now go back? If I got f triple prime, how do I get to f double prime? Is this process reversible? And that's an interesting question, and this leads us to the concept of the antiderivative. Such an important meaning in actual everyday life, including physics, engineering, biophysics, you name it, it's there. Okay, so let's look at how we can reverse the process of differentiation. Okay, so I want to introduce to you the definition of an antiderivative, and it's a very simple one. You see, we're looking for a function whose derivative is this function f of x. So it says an antiderivative of a function f of x, which you're so familiar with, is a function capital F of x, such that f prime of x leads to that original function. So it's difficult to look at a definition, so I want to try a few examples, illustrative examples, that's what we'll call them, to see what we come up with. Okay, so interestingly enough, what all we're doing is we're trying to reverse the process of differentiation. But it's not straightforward, not straightforward. We also got to keep in mind that the derivative of a constant is 0, and that's going to play a very, very important role in finding antiderivatives. Simple function f of x. Okay, what are you going to call it? F of x equals to x. Simple, keep it straightforward. Now, what is the antiderivative of f of x? I'm looking for a function. Now, think about this carefully. I'm looking for a function whose derivative is x. So let's think about that very carefully. The derivative of x squared is 2x. So that's not the function we're looking for. But what if I told you that the function f of x or one of them, is x squared over 2. So from our knowledge of differentiation, what is df dx? Haha, and it works out. Okay, now the point is, you know what, is this a guessing game? No, mathematics is not a guessing game. So there are rules and laws in place that help us identify these antiderivatives. But remember I mentioned something about a constant. So what if I gave you another function? I want to call that g of x. And that function is x squared over 2 plus some constant. What is the derivative of g of x, g prime of x? It's also going to be x. Why? Derivative of x squared over 2 is 2x over 2, which is x. Derivative of constant is 0, and there we have it. So g prime of x is obviously f of x. So now what I'm claiming is I have a family of functions, whose derivative is x, as long as that constant is arbitrary. So for different values of the constant, I'm just going to produce a family of curves. And you can see straight away what that curve is. If I had to ask you to plot x squared over 2, it's a parabola centered at the origin. And then as c varies, say c1, c is 1, c is 2, c is 3, we have vertical displacements. And we have a family of curves. But the derivative of each of those is always going to be x. So that is pretty cool. Okay, so the antiderivative is not a unique function. It depends on that constant. Excellent. Okay, let's draw on our knowledge of the derivative. And if you recall, after studying differential calculus, if I got a function f of x equal to sine x, what is the antiderivative of sine x? I'm looking for a function whose derivative is sine x. That's what I mean. Whose derivative is sine x. Now, if I differentiate cos x, I have a problem. It's minus sine x. So what do you think the antiderivative of sine x is? The antiderivative of sine x naturally is minus cos x. But don't forget, there's always going to be a constant. Because if I differentiate f, capital f prime of x, that's going to be minus into minus sine x, because the derivative of cos x is minus sine x. The derivative of the constant is 0. And guess what? For show as God made little apples, minus and minus, and I get f of x. So it's important that you review your derivatives, especially of these trig functions, exponential function, the log function, those special functions that we learned earlier on. Don't forget them. How can you forget mathematics? It's part of your DNA. I just don't understand how a student would go from grade to grade or course to course at university and then try to forget the work they've done in the previous 6 months. That is not the process of learning. If you learn that way, you're setting yourself up for failure. Learn for life, not for an exam. Okay, so now guys, this is important. I mentioned notation, so here we go. The set of all antiderivatives of a function f is the indefinite integral. Now this is also very important. I'm using the word indefinite integral of f with respect to x. And this is that function we call f of x. So the integral of f of x dx, in other words, in plain and simple English, the antiderivative of f of x dx is equal to capital F of x plus a constant. Now this is interesting because if I differentiate both sides of this thing, what does it tell me? It tells me if I differentiate both sides of this, I will get, think about that carefully. Just want to remind you with respect to x, yeah, ddx of this thing, the integral of f of x dx, integral, that's what it's called, integral, is equal to d of f dx plus dc. Is that a d? Right, neatly dx, but we know that is 0 anyway. So what it tells me, what I've just proved, is f of x is nothing more than f prime of x. So it tells me that capital F is the antiderivative of little f of x. And the only way you can appreciate this is to do lots and lots and lots of examples, all right? And not forgetting the constant every time. Instead of saying anti-differentiate, we'd rather say when we integrate. I think that's important. With the power rule in when it comes to differential calculus, to reverse the process. How does it work? Well, recall for differential calculus. Look at that D, right? Neatly. In differential calculus, we said that d dx, say, I'll give you an example of x cubed, is what? We know it's 3x squared. The rule tells us drop the index to the front and subtract 1. So we also know in general that d dx of x to the power n, drop the n to the front and subtract 1 from the index. Obviously, there's conditions on what x can be or what values x can take. Now, what happens to integral calculus? We're going to go the other way. And this is a very, very powerful rule. And that's the reason why I'm spelling it out, because you'd use this on a daily basis. So if I'm integrating, going the other way, of x to the power n dx, I'm looking for a function whose derivative is x to the power n. That's the important thing. That turns out to be, this is very interesting, instead of subtracting 1, you add 1 to the index. Instead of throwing it to the front, you divide. And don't forget to add the constant. Absolutely important. Okay? Think about that carefully. The integral of x to the power n dx is x to the power n plus 1 over n plus 1 plus a constant. If I differentiate the right-hand side of down in that beautiful blue, I'll get x to the power n. So don't forget the power rule. And it's something that's going to be very common in your tests and exams. So learn and understand. Okay, so let's look at some examples. So the first example I'm going to look at is x cubed dx. I'm looking for a function whose derivative is x cubed. The rule says, is there an x? There's an x. Add 1 to that and divide by the resulting power and add a constant to it. So this becomes x to the power 4 over 4 plus a constant. To check your answer, if I differentiate the right hand side, I get x cubed. I'm on track. So that's very, very important. Let's try another one. Let's try fraction. But these guys are normally disguised. Examiners can be really cruel people. I'm not sure why they are like that. So the square root of x dx. But now we smart. X to the power half dx. Yay, we got them. X to the power half plus 1 all over a half plus 1. You're adding 1 to the power. That's what the rule says. Don't forget the constant. It's called the constant of integration. Constant of integration. So 1 becomes 3 over 2. This becomes 3 over 2 plus a constant. This is so much of fun. You're dividing by 3 over 2. It's same as multiplying by 2/3. 3 over 2 plus a constant, and there's your 1 mark in the exam. It looks difficult, but it's not. It becomes part of you, part of your DNA as you work through this and you start to enjoy it and you start kicking it, you know. You're in the zone. You're in the integration zone. It's sweet stuff, man. Okay, let's do a few more for the neighbors. You know, that's always share your knowledge. That's the important thing. So I want to try something like the integral of 1 over x squared dx. What is that equal to? Well, we can write that as x to the minus 2 dx. And this is solved because x to the minus 2 minus 1, well, not minus 1, you're going to add 1 to it. And then you're going to be minus 2 plus 1 plus a constant. So what does that become? That becomes x to the minus 1 all over minus 1 plus a constant. And we know this becomes minus 1 over x plus a constant. That's the integral of 1 over x squared dx. So now let's look at something else and something more interesting. Let's take something like the integral of 1 over the cube root of x dx. We're too smart for this, man. What is this? 1 over x to the power 1/3 dx. The dx basically means we are integrating with respect to x. All right? So this becomes the integral of x to the power minus 1/3 dx. And what does the rule say? It's minus 1/3. You got to add 1 to it, divided by minus 1/3 plus 1 plus a constant. And that becomes x to the power 2/3. It's amazing how that simple algebra that you learned way back in grade 5 comes on. Like, what is minus 1/3 plus 1? That's plus 2/3 plus a constant. But don't forget, we got minus 1/3 plus 1 is 2/3. And we can tidy this up. And the final answer is 3 over 2. X to the power 2 over 3 plus a constant. And there's your 1 mark. Super duper, guys. Absolutely amazing. Fractional powers, all of that works really well. But let me introduce you to something very, very special in the next slide. Hold on to your boots. That's my question, if you remember. dx of 1 over x. You'll remember the power rule. That is ddx of x to the minus 1. And the rule says drop the minus sign to the front. Take the x and you subtract 1 there. So the answer is minus x to the minus. Whoa, what happened to the 2 there? It's minus x to the minus 2. Don't worry about that part. And this becomes minus 1 over x squared. I think everyone's happy with that. So the derivative of 1 over x is equal to minus 1 over x squared. Now, the question is, if I had to reverse the process, so it tells me that the integral of minus 1 over x squared dx. Let's check that out. Don't let that minus sign confuse you. You can actually take that minus sign out because it's a constant. It's 1 over 1 over x squared dx. And that becomes minus integral of x to the minus 2 dx. And that becomes minus, we're going to add 1 to the power. The result will divide, don't forget the constant. So this becomes minus 2 plus 1. So that's minus x to the minus 1 and minus. So it becomes x to the minus 1 all over minus 1 plus a constant. And so the answer turns out to be 1 over x plus a constant. So if c is 0, so we get exactly what we found over there. Okay, so the integral of minus 1 over x squared dx, one possibility is 1 over x. Here's the big question. What is, and I want you to think about this, I'm going to square this out here. Square that out? That's not a square. But anyway, what is the integral of 1 over x dx? Homework for you. What is the integral of 1 over x dx? Think very carefully. Google, phone a friend, you're an aunt or uncle who's in mathematics, give them a call. Send an email to NASA. I don't know. 1 over x dx. Let me know.